Hello everyone, today I'll be presenting about my work with the Design for Excellence lab on a tuning countermeasure for power side channel attacks. With the growing role of technology in our lives today, there are many avenues of attacks for malicious actors, and several of these attacks target hardware and exploit physical access to devices, and the side channel attack is one such attack. These side channels exist because of information leakage caused by the physical reality of the chip. A power side channel, which we see on the left here, involves monitoring power consumption of hardware and performing statistical analysis of the slight variations in power consumption and extracting sensitive data. The figure on the right shows the process, which is having a chip perform AES encryption, measuring the power consumption using an oscilloscope, and performing correlation power analysis, which is the statistical analysis we use. We saw that previous works explored countermeasures based on VCC tuning, which is a mixing of high and low VCC, to protect against power side channel attacks. But there's not been much work done on cell driver strengths, despite these having an impact on the power profile as well. Looking at these power profiles for an AES core, we saw that changing driver strength affected the power profile and thus would affect the effectiveness of a VCC tuning countermeasure. So we decided to do a study to better understand the effects of changing driver strength, and we also decided to look into tuning the driver strength and the VCC together. In our study, we implemented this runtime tuning on ASIC and FPGA to see how this would work on different setups. To see more details on the implementation, you can refer to the longer presentation. These are the results for the CPA trials on our ASIC setup. For more detailed analysis of each of these scenarios, you can refer to the longer presentation available. The resilience here is measured by traces to disclosure, which is the power traces needed by the attacker to identify the secret key. Scenario 1 here is the untuned baseline, which is the default setting. Scenario 2 is static tuning, where driver strength and VCC are set to static values, and this shows no improvement. Scenarios 3 and 4 are dynamic VCC tuning, and this already shows significant improvement over the baseline, which is in line with previous work. Scenarios 5 and 6 represent dynamic driver strength tuning, and we see how driver strength tuning actually shows an improvement over its VCC tuning counterparts, because 5 is better than 3, and scenario 6 is better than scenario 4. Lastly, scenario 7 represents all dynamic tuning, which is dynamic VCC tuning combined with dynamic driver strength tuning. And this shows the best resilience, justifying our intuition that driver strength tuning could be a useful tool to improve security against power side channel attacks. So to validate our conclusions from the ASIC test, we also tested on an FPGA implementation. First, we need to note that the bounds are different. Here, the bounds are much larger values. Scenarios 1 and 2 are the untuned baseline cases, which again are the default cases. Scenarios 3, 4, 5, and 6 are all the results from static tuning, and these all show a large drop in resilience actually. And this shows us that static tuning is counterproductive here because there's actually an increased information leakage because of the toggling of the input-output pins to implement the tuning. After the static tuning cases, we looked at dynamic driver strength tuning. Scenario 7 here is low VCC driver strength tuning, while scenario 8 is high VCC driver strength tuning. And again, we have to notice the difference in the bounds here. So these again are much larger. Scenario 7 is in the range of 28,500 traces, while scenario 8 is in the range of around 60,500 traces. And this shows the effectiveness of dynamic driver strength already, but we also have a ninth scenario where we implement the dynamic driver strength tuning and dynamic VCC tuning, so joint tuning. And in this case, we had 170,000 traces, but none of our 100 CPA trials could break the resilience of the scenario. Since we don't know how many traces it takes to break this case, it shows that joint tuning is at least 11.8 times as resilient as the untuned baseline, which is an improvement over the baseline, but also over the other tuning cases as well. Using our results, we performed a layout analysis and got some takeaways for design guidelines. You can see the details of this analysis in the longer presentation. To summarize our takeaways, we saw that static tuning is ineffective and even counterproductive in cases, that dynamic VCC tuning is promising but limited, while dynamic driver strength tuning is the most effective and preferred over VCC tuning, as VCC tuning requires additional tuning features and is also less resilient. For tuning of the flip-flops, we saw that tuning all flip-flops is only possible when in ASIC high layout overheads are acceptable, and possible in FPGA only when enough input-output pins are acceptable. An alternative is tuning only the flip-flops associated with the AES text, which is what we did in the FPGA case, and it proved to be effective. In this study, we examined what role driver strength tuning could play in countering power side channel attacks. More work could be done to make the tuning implementation more efficient by using ASIC circuit level primitives for implementation and maybe finding an optimized input-output pin assignment strategy for the FPGA implementation, because in our case, we just randomly used unassigned input-output pins. Future work could also study how driver strengths and VCCs affect leakage power profiles to help us understand how leakage power attacks could be effective against these tuning implementations. This wraps up the presentation, and thank you for your attention.